So bivariate data. What is bivariate data? The first thing, it involves two variables, like x and y, for example, or a and b, or it could be any particular letter which represents some kind of variable, important function, or anything else. It also looks at the relationship between the variables. So how do they relate? The relationship between these variables. We then analyze or form an analysis of them, and we end up with what is known as correlations. So a comparison using a graph. The correlation can be positive, negative, or no correlation. And every graph has a certain type of correlation that you can. There are also analysis of data using tables. We could also use box and whisker plots, interquartile ranges, median comparisons, mean comparisons, and normally we have to collect data and form some kind of analysis of this. So the concept of this is that we have to collect the data and then after that analyze it, come up with some kind of conclusions in order to answer a specific question. All right. Now remember, data can also be qualitative. All right, qualitative, or it can be quantitative. Qualitative means that it has some kind of quality to it. So an example of qualitative data would be something like something that can be counted or measured. Okay, qualitative data, you're looking at stuff like I have brown hair and my friend has black hair. I have green eyes, he has blue eyes. I am funnier, he is louder, or she drives a red car and her friend drives a blue car, or anything on the lines of something that has a quality to it. Now, quantitative data is something where you actually have an amount to it. So you're looking at comparing the heights of two people, the weights of two people, the fact that you live certain distances from school, and you compare that as well, or how often you go swimming, or anything on those lines as well. And you can compare data in that sense using qualitative or quantitative means. So the first step is to collect the data. Let's suppose we collect some set of data, X and Y, and I'm not going to specifically say where is it from, okay? But let's just say I collect X and Y, and I'm going to put some random values in here, okay? So 2, 4, 7, 8, 9, 10, 14, 20, 5, 7. All right. Let's suppose I've randomly collected this data, which doesn't really have a story to it, doesn't have a question to it, but it's some set of data. X represents some variable, Y represents some variable. So this is just a bit of a quick collection of data. Okay, this is in short, quick short summary of bivariate data. We've got two variables, so bivariate data. The next thing I want to do now is plot it. Okay, so I have the y, let's say on the y-axis, and I have the x on the x-axis. Sometimes I can interchange it, but in this particular case, I'm going to keep y on the y-axis, let's say. We normally put the independent variable on the x-axis and a dependent variable on the y-axis. But in this case, I haven't even given you a story, so it's just the concept. So we're now plotting this, right? My y value, the highest it goes to is 20. So I'm just going to provide some values, 20 and 10. My x value, the highest it goes to is 14. So I'm going to go up to 16, 8, etc. And then it will be 5 year, 15 year, 4 year, and 12. All right, now if I go 2 to the right and 4 up, okay, 2 to the right, which is over here, and 4 up, I will end up over there for that first point there. 2 to the right and 4 up. Then I go 7 to the right and 8 up. 7 to the right, this is 5, 6, sorry, that's 6. This will be 7, and then 8 would be somewhere here, and it would end up over there. 9 to the right and 10 up. 9 to the right, this is 10, so 9 is over here. Okay, so 7, and that was 8. So 9 and 10 will end up slightly above there, in line with 9. 14 to the right and 20 up. Will end up just about there. Now the data set doesn't really form a straight line. I've got one more left though. Let's go 5 and 7 up. 5 is over here and 7 is slightly above, but more or less in the middle here somewhere. Okay. Now, if I draw a line through this set of data, and we call this the line of best fit. The line of best fit is best drawn when you have the same number of dots on either side of the line. Okay. So the line of best fit in this case, we can count 2 dots on this side, 1 and 2. On this side, we can count 1, 2, 3, but this one is slightly further away. We could adjust the line, and this can also be calculated using a certain formula. So if I adjust the line so that I can have the same number of dots above the line and below the line, then I'm looking at possibly something that will look like that. That looks like a line that would be going through most of the data on either side, like that. I could tilt it slightly this way and bring it up slightly this way as well, like that, maybe. I've got slightly 2 on either side, but that would be more or less a line of best fit, let's just say. Let's do that what it was, okay? Not super accurate, but just an idea. So what is that called? That is your line of best fit. And what do we notice about this line of best fit? It has a positive gradient. And a positive gradient, which is sloping upwards, means that the relationship between, we can form some kind of conclusion here, the relationship between x and y is positive, number one. Is it a weak positive or is it a strong positive? Because the points are quite close to the line of best fit and not far away and moving together in the same direction. Strong positive. Right. This is going to be a strong positive relationship between the two. Okay. So we've got a strong positive because they are more clumped together than if they were weak. And as x increases, so does y. If we have our line of best fit, we can then form some kind of conclusions. We can find predictions. So I could choose a point, like let's say, I want to find out what number will y be if x is 12. Okay. So let's suppose this graph continues and I'm given x is equal to 12, and I want to find out what is y going to be. I go to 12, and I work my way up, probably with the ruler in a straight line, to the line, which is going to help me predict this trend that's taking place. And it looks like it's going to be close to, if not 16. And I can form predictions now on the trend of x and y using my line of test squares as well. So if x is equal to 12, then y is equal to 16. I can also find the gradient and actually find the equation of the straight line. Because it's a straight line, I could possibly do that. It's not going through 0, 0, but let's say it was going through a point here perfectly at half, which means I can create the equation of this line now by taking 2 points. If I take this point, which is 12 to the right and 16 up, and I take this point over here, which is a half to the right and 0 up, I could take those 2 points and find the equation of the straight line, which means I need the gradient, which is my m value from y equals mx plus c. And that's the change in y over a change in x, which is going to be 16 minus 0 divided by 12 minus half. That'll be 16 over 11 and a half. Obviously, a calculator would be really useful right now. So 16 divided by 11.5 is 1.39. So my gradient is 1.39. I substitute that back into my equation, and I get, therefore, I get y equals to 1.39 x plus c. And I now need to substitute a point in there to get c. Let's suppose I substitute a half and 0 in there. So x will become half and y will become 0. So I end up with 0 equals 1.39 times half, which is equal to 0.695 or 0.7, let's say 0.7 plus t. So therefore my c value is negative 0.7 by substituting that point in there. And that gets me my final equation. So this entire part over here is all to do with the equation. So therefore my equation will be y equals m, which is 1.39 x minus 0.7, and that would be the y-intercept right over there, negative 0.7. So I've got the equation of this line now, which is y is equal to negative 0.7, but 1.39 minus 0x minus 0.39x minus 0.7. The part where we had the relationship between strong and positive, this is known as your correlation of the data. And a correlation can have many different forms. So let's have a look at the concept of correlation. If you're given data trends where they're very close to each other like that, and we can draw a line where it's quite close to all the dots, it would have a strong positive correlation. If you have data sets which is in the opposite direction, then we would have a weak negative correlation. Well, in this case, it's actually still strong. Let's keep it strong, and how would I do that? Only keeping close to each other so that they actually look like if I draw a straight line through, they will be close to each other. I'm going to keep it as strong negative. Notice this one has a negative slope. This one has a positive slope. Let's draw a weak positive one, which means in this case, the points that we find are far from the line. So this is a weak positive correlation. And then if I go backwards, this would be weak negative correlation. When the data set is like moving as a straight line like that, you can see that there is no correlation. Or if it's going all the way down, almost straight line going down, there's no correlation of there either. And the last possibility is if the data set is scattered where you don't even know if you must draw the line this way, that way, that way, you're not sure which way to draw the line. In this case here, we would say there's also no correlation between that. All right. Now, we also have what is known as a correlation coefficient. The correlation coefficient is basically some kind of measure of the relationship between two data sets. So a correlation coefficient, just to touch on the concept of it here, a correlation coefficient is a value, it's a numerical measure of the type of correlation between two variables. And we basically have a positive correlation, which means they'll basically move in the same direction, like these two. And a positive correlation close to 1 would lie very close to the line. A correlation which is slightly further, this could be slightly away from 1. Let's say on a number line, if I had -1, 0, and 1, this would be close to 1. If I had -1, 0, and 1, this would be close to sort of in the middle over there. What you notice is that I'm starting from -1 and I'm ending off at 1. And that's the correlation coefficient. It starts from -1 and it ends at +1. On this side over here, -1, 0, +1. This is a negative correlation, a very strong negative correlation. Close to 1, probably not exactly. If it was exactly 1, it would be a perfect straight line. And this one here, slightly further away, which is going to be around 8. Whereas this one here at the bottom, which has no correlation, will be very close to 0 on either side. All right, and that's known as a correlation coefficient. There is a formula for this. That formula is calculated probably in another book. We can work through that, or another lesson we could do that. But there is a certain formula that we use which is known as the Pearson correlation coefficient. And you have to have the sum of squares, the sum of x times y, which is all to do with some calculation that gets you this value here. But just to touch on the idea that this is a strong positive correlation, and correlation coefficient exists where you can actually measure this data. So we're looking at, let's go back quickly, bivariate data. We know what correlations are. And we can then take our data and we can also express it as box and whisker plots. Right, box and whisker plot. It looks like that as well. Let's have a look at a quick summary of a box and whisker plot and what or just a reminder of what it is. Your box and whisker plot will start from a minimum value, and then we'll have your first quartile, which is 25% of your data, and then another 25% gets you to median, another 25% gets you to the third quartile, and another 25% gets you to the maximum. All right, this is known as your lower quartile. This is your median, your middle value, and this is your upper quartile. And then we have our interquartile range, which is calculated by taking Q3 minus Q1. And when we subtract those two, we end up with the interquartile, what is known as the interquartile range. Given the set of data that we have over here, we had to find the interquartile range for this set of data. We'd have to divide it into maximum, minimum, etc., and then compare it. We could compare each one separately, x's first and then y's, or we could bring it together if we need to by some or other means, depending on the type of question we get. All right, so that comes in with interquartile range as well, median. And don't forget your mean is your average, and median is your middle value. When we compare medians, you can also tell a lot from it. You can tell whether the data set's middle values lie in a certain, there's so much of information that you can get from comparing two box plots, for example, box and whisker plots. So an example would be, let's say I've got a classroom of, say I've got a range of values of marks starting at 0% and going all the way to 100%, okay? Class A box plot looks like this. Class B box and whisker plot looks like this. We can see that the median is lower for class B than it is for class A. And that would be over here, Q2. And that would be lying roughly around 50%. This is going to be like roughly around, let's say, 60%. That's not the average, that's the middle value. When you're drawing a box and whisker plot, let's suppose this class or each class had a different size. This all had the same size of 24 students. Okay? So the class size is given as 24. This means that 6 students got between those two marks. 6 students got between those two, and those two. Likewise over here, because 6 times 4 is 24. And if I have to maybe predict, just looking at my line that I produced here, this looks like it would be around about maybe 18% was the lowest mark here. And 6 people got between 18% and let's say 38%. Over here, this would be 44% maybe. This one here, and just gauging more or less, just to give you a quick idea of comparing two box plots. This is going to be 25%. This one over here is, and this could be the first variable, this could be the second variable where we're comparing bivariate data, right? Comparing two classes, maybe. Is there a correlation between the marks in one class and the other class? We'd have to use an XY table, let's say. This one here is 60% we got there. This one is 50% we got there. And then from here we got 66%, 74%, 80%, and this one here is got 90%. So class B has a higher average, right? But you can also notice, just looking at this, 12 of the half of the class got between 38 and 66%. Whereas the other one, half of the class of the year, got between 44% and 74%. And we can see that the median is higher for class A. Class A might not have got to 90%, but definitely we can see that most of the students are more clustered around the median. Everything is more closer to the median than class B, where there's more extreme results in this case. So this would be more extreme marks. Somebody getting a really low mark, somebody getting a really high mark. This one is less extreme values, maybe even less outliers. Overall, the performance of Class A is better because the entire region is higher than that entire region. 50% or more, 75% of the class, definitely 50% of the class is slightly higher than Class B in Class A. We could then measure the performances between the two as well, and also talk about the differences in the medians and how they affect that. All right, so that would be an idea of that.